So let's suppose we have an angle here, theta. Theta's measure you can see is positive. It's going to be greater than 2 pi radians. Terminal side ends up there in the first quadrant. And I've got a point on that terminal side, x, y. We're going to talk about an angle that's a reference angle for this angle theta, being the acute angle drawn from the terminal side of the angle to the closest x-axis ray. And that would be right here. So my reference angle, if I were to sketch it out again, looks to be this angle right here. And on that note, I still have the same x, y point here on the terminal side, because the reference angle, which is acute, is going to have the same, it's coterminal with my angle here that's greater than 2 pi. So again, a reference angle is always acute. It's always between 0 and pi over 2, or 0 and 90 degrees, and it's drawn to the nearest x-axis, each side of the x-axis. So we'll look at another example here. So here theta will have a negative measurement. Note I've gone clockwise around. Terminal side is in the second quadrant. My reference angle is going to be drawn from the terminal side to the nearest x-axis, and the nearest x-axis in this case is going to be right here. So my reference angle is going to be this acute angle right here. And again, if I were to put that acute angle, relocate it in the first quadrant, it's going to look something like this. So if I've got say 42 degrees here from my terminal side to my x-axis, I could locate that angle here and put it in the first quadrant as, say, a 42 degree angle here. So again, the reference angle is drawn to the nearest acute angle to the nearest x-axis. One more example. So suppose you're asked to find a reference angle for an angle whose measurement is 290 degrees. So 290, I'm going to go around past 270, 20 degrees past. So I'm 20 degrees here. The nearest x-axis ray is right here, so my reference angle is 70 degrees. So my reference angle for a 290 degree angle is 70 degrees. Okay, so let's suppose we put a pi over 4 or 45 degree angle in standard position here on my unit circle. Here's my pi over 4 angle, and here's my unit circle radius 1, and I'm interested in what the coordinates are of that point on the terminal side of the angle, so I can get that x and y coordinate, which will be my sine and cosine for pi over 4. To help me do that, we go back to geometry class, remembering that if I have an isosceles right triangle with a hypotenuse of 1, I can use the Pythagorean theorem. We've done this a number of times this year. X squared plus x squared equals 1 squared. And when I solve that, eventually, doing a little algebra, I get x equals root 2 over 2 in simplified form. And I'll let you work on that on your own if you wish to work it through. And so therefore, I can label these sides here root 2 over 2 and root 2 over 2. And so here's my pi over 4 degree angle, and I go over root 2 over 2 and up root 2 over 2. And over here you can see if I drop that altitude in here, here's my 45, 45, 90 right triangle, so I can label the points on the terminal side that coincides with the unit circle is root 2 over 2. And therefore I know the sine of pi over 4 is root 2 over 2, and the cosine of pi over 4 is root 2 over 2. Now, that's useful because from our idea of a reference angle, what that allows us to do is to find the sine and cosine very quickly of any angle whose reference angle is pi over 4. For example, if I give you a 3 pi over 4 angle to here, let's say that's 3 pi over 4, and I consider going out here onto the unit circle, what are the coordinates of the point going to be on the terminal side? Well, my reference angle here, remember, is going to be pi over 4, and so I'm going over left, negative root 2 over 2, and up, positive root 2 over 2. So negative root 2 over 2 and positive root 2 over 2 will be my coordinates for the point on the terminal side out 1 unit on a 3 pi over 4 angle. If I were to go, say, to spin around to 7 pi over 4 down here, and I'm on the unit circle here, what would the coordinates of that point be? Well, I'm going over right pi over 2, or root 2 over 2, down root 2 over 2. So I'm going to get root 2 over 2 to be my x-coordinate, negative root 2 over 2 to be my y-coordinate. So any angle pretty much whose reference angle is pi over 4, and my reference angle for 7 pi over 4 will be pi over 4. The reference angle of pi over 4 is going to allow me to get the coordinates labeled on the unit circle, 1 unit out from the origin on the terminal side of the angle. And again, these numbers, root 2 over 2, negative root 2 over 2, is reference angle sine and cosine values for any angle that comes out as a multiple of pi over 4 needs to be memorized. So what we've done with our pi over 4 angle, our 45-degree angle, we now also want to do with angles that are multiples of pi over 6 or pi over 3. And to help us do that, again, we go back to geometry class. We consider an equilateral triangle, and an equilateral triangle will have 3 60-degree angles. If I come in and drop an altitude to one of the sides, that altitude, we remember from geometry, is going to bisect the top 60-degree angle. So I get these two 30, 60, 90 triangles. So from one of these 30, 60, 90 triangles, we're then going to be able to use the Pythagorean theorem and get our point. And we do it as follows. In our original equilateral triangle, let each side be 1. That altitude that's going to come down is going to bisect the base to be a 1/2. Note, opposite the 30 degree, I'm going to have a length of 1/2. So here's my 30-degree angle. Opposite that is 1/2. Opposite the 90-degree angle, I have a 1, and all I need to do is solve for the missing side using the Pythagorean theorem. X squared plus 1/2 squared equals 1 squared. And I do that, and I get root 3 over 2. So that means, then, that I can label my points on the unit circle on the terminal side of an angle for a pi over 6 angle. Pi over 6 is 30 degrees. Out here, if I'm seeing that 30, 60, 90 triangle, the coordinates here are going to be, let's see, opposite the 60 is the root 3 over 2, and opposite the 30-degree angle, the pi over 6 angle, is 1/2. And consequently, if I look at the pi over 3 angle, things are just going to reverse. If this is my pi over 3, my 60 coming down, this is going to be my 30. If this is 1, opposite the 30 is 1/2, opposite the 60 is root 3 over 2. And again, so if I'm on the point on that terminal side that lies on the unit circle, coordinates are going to be 1/2, comma, root 3 over 2. And again, do these need to be memorized? Absolutely. Next slide, summary. Now, to help me keep track of this, you got 5 numbers to keep track of for sines and cosines. 0, 1, 1/2, root 2 over 2, and root 3 over 2. And obviously you got to keep track of negative signs depending which quadrant the terminal side's in. You're obviously keeping track of 10 numbers, 9 numbers. 0 is neither positive nor negative, plus or minus 1, plus or minus 1/2, plus or minus root 2 over 2, etc. So how do I help keep track of which number is which? Well, I think it's pretty easy. Multiples of pi over 4, you got root 2 over 2 for both your x and y coordinates. That's not very difficult. So the question is, how do you keep track of, for the 30, 60, which is the 1/2 and which is the root 3 over 2? And visually, this should help you. Consider, I've drawn over here a 30-degree and a 60-degree angle relatively to scale. Each one's to scale. And I want you to look and compare the distance here and the distance here if I draw this somewhat accurately. Clearly my 30 is under 45. Which distance appears longer? This x or this y? And clearly that distance appears longer than this distance. Which number is bigger, root 3 over 2 or 1/2? About 1.7 over 2, certainly more than 3/4, or about 2/4. Clearly the 1/2 is smaller. So if I look at these two distances, that distance is less than this distance. That's my 1/2. That's my root 3 over 2. So for the pi over 6 or 30-degree angle, I got root 3 over 2 and 1/2. Conversely, for the 60-degree case, if I'm looking here and I draw this, I actually haven't drawn that very accurately. We actually should go up a little further, but if I look at this distance here relative to this distance here, which is longer, clearly that is longer than this, and on the other hand, I just know that those numbers reverse, so for the 60, it's going to go over 1/2 and up √3/2. Now, the final, one of the applications that you're going to learn in this section, which is kind of cool, is talking about latitude. And if I say, for example, what is a point on the Earth's surface that's at 50 degrees north latitude? It means from the center of the Earth, draw out to, say, the equator, a segment, and then if you then, and we're going to call that particular segment there a terminal, an initial side, sorry, of an angle, spin that initial side up to a point, spin it 50 degrees in the north direction, wherever you wind up on the Earth's surface, we're going to say that that point is 50 degrees north latitude. And note there are a whole bunch of points on the Earth's surface up here that are going to be, you'd be able to spin, come out from the equator, come out to the equator in multiple places certainly, and then spin up that 50 degrees north. So that's why lines, or we call circles of latitude here, appear on the globe. And they're going to distinguish either spinning up and getting into the northern hemisphere, 50 degrees north, going up, or if you take your initial side and rotate down into the southern hemisphere, they're going to call that latitude south. So for example, coming down here toward the South Pole, if I come down 73 degrees, and I'm going to call that 73 degrees south. And again, note, there are infinitely many points on a circle of latitude down here, such that if I were to take a radius of the Earth coming out to the surface and spin it down along the surface to a position of so many degrees, I get a whole bunch of points that are 73 degrees south latitude. And obviously then, for locating position on the Earth, we could do the same thing with longitude, and we would have great circles of longitude going around the Earth, and where a circle of longitude intersects a circle of latitude determines a single point. So that's a little bit on latitude and longitude, and the book gives you a fairly complicated example. The homework problems are much simpler than the sample problem in the book. The sample problem in the book is they made up a nifty little problem, but the homework problems are much easier.